Okay, so this is going to be more review of some problems in chemical kinetics, this time focusing on problems involving integrated rate equations. Again, I'm starting with some problems that I borrowed from a chemistry text, Chemistry by Riddell and Navidi from West Publishing published in 1990, a book that I had on my bookshelf. So let's look at some problems. Right? So let's remind ourselves about integrated rate equations. Right? What we think of as rate equations are differential rate equations. They describe the rate at a moment. But if we integrate those over time, we get different equations. Right? So for zero order, if we integrate that zero order rate equation over time, then you get something that looks like this, right? That the concentration of A minus the concentration of A at the initial time is equal to minus KT. And if we convert that into a linear equation, then we get that the concentration of A is equal to minus KT plus the concentration of the initial concentration of A. So if we do this, right, we get a y equals mx plus b form, right, where the concentration of A is our y variable, the elapsed time is our x variable, our slope is the negative of k, and the y-intercept is the initial concentration of A, right? And so we can, using this, we can look at, we can follow a reaction, the concentration of the reactant with time, and the slope tells you what k is if it's zero order, right? For a first order expression, when you integrate that first order expression, right, where A is raised to the first power, you get a different equation, and you get something that looks like this, that the natural log of your final concentration of your reactant divided by the initial is equal to minus KT, right? And if you reorganize that, right, remembering our log rules, the left side would rearrange to the natural log of A minus the natural log of A 0. And I hope I have enough room here, right? So if we reorganize that into a linear form, you get that well, let me just clear some space. I've shown you that. So let me clear that space out. Right? So we end up with our linear form is that the natural log of the concentration of A at any time is going to be equal to minus KT plus the natural log of A0, which is again in a y equals mx plus b form, where the natural log of A is your y variable, time is your x variable, the negative of k is your slope, but the units of that slope would be different because they're the units of a first order rate constant, and then the natural log of your y-intercept is the initial concentration. If our reaction happens to be second order, right, a second order expression, then our integrated rate equation would take an even different form. It's 1 over the concentration of A minus 1 over the concentration of A0, or the initial concentration, is equal to K times time. If we rearrange that to make it a linear equation, 1 over the concentration of A is equal to K times time plus 1 over the initial concentration of A. So again, we get a linear equation, but in this case, 1 over the concentration of A is our y variable, time is our x variable, right? And so we can tell if we have a set of data, right, the data all look similar just to observation. But if we plot the concentration of A versus time and get a linear equation, we're zero order. If we plot the natural log of the concentration of A versus time and get a straight equation, we're first order. If we plot 1 over the concentration of A versus time and we get a straight line, then we're second order. So we can use these plots of concentration versus time data to determine our reaction orders. So we'll show a couple of examples of that. Okay, so here we have a reaction that is tertiary butyl bromide reacting with water to give tertiary butyl alcohol plus hydrogen bromide. And here we have, right, some time data. In this case, the data is given in hours, and as time elapses, we're measuring the concentration of our reactant tertiary butyl bromide. And so I took this data and I put it in Excel and I plotted it out. And so I got plots that look something like this, just to sort of give you a quick view. All right, so let's pick that's a fine color there. All right, so when I plotted it against zero order, right, I got a plot that looked like this, where I have time and I have concentration over here, and I got my dots sort of doing this, so when I tried to draw a straight line through them, it sort of cut through like that. Okay, so not linear, not zero order. Okay, and so when I plotted it against the first order equation, right, so I plotted the natural log of concentration versus time. That gave me nice points. My lines seem to go through them. And so we'll keep first order in the mix, but let's check to see what the second order one looked like. So when I plotted 1 over the concentration versus time, I got points that looked like that. And when I drew my line through them, it clearly didn't fit, right? There was a curve there that didn't fit. And so that argued that first order was my order. And when I looked at the equation, my slope of that one, the slope was equal to negative 0.0522. 0.0522. And the units of that slope would be, let's see, it's rise, which has no unit, divided by run, which would be time, so that would be 1 over time, right? Right? And since my time is in hours, so that would be per hour. Being clear, let's straighten that up. Right? Per hour. If we go back to our integrated rate equation for a first order process, right, it was that the natural log of the concentration of A, right, was equal to minus KT plus the plus the natural log of the concentration of A0, right? We have that. So the slope is equal to the negative of the rate constant. So therefore, K is equal to 0.0522 per hour. And that's the rate constant for that first order process given in the proper units. Okay? So here we have another one. This is the rearrangement of the ionic compound ammonium cyanate to form urea. This is the reaction that Friedrich Wöhler did to first prove that you could make an organic compound, something that was from a living thing, from non-organic, non-living precursors, right? Urea is a compound found, made by living things. So this reaction was an important one. And so I was given, this, time data in minutes and concentrations of ammonium cyanate, as in molarity as time changed. And I again did all three plots, okay? So when I did the zero order plot, that is concentration of ammonium cyanate with time, I got something like that. And when I had the computer try to draw a line through, clearly there was a curve, all these points lie on one side of the line, points on either end lie on the other side of the line. That's not a good fit. So I tried the first order, and when I did the first order, that is, plotted the natural log of the concentration versus time, I got a better fit, but still, when I drew that line through, it looked like there was a curve, My R was okay, but I still wasn't sure. So I went to the second order process, where I plotted 1 over the concentration of my reactant versus time. And on that one, I got a nice straight line. And so I was confident then that it was second order, and my slope was 0.0502. 0.0502 was my slope. And the units of that slope, this would be 0.0502 per molar, rise per minute. Okay? And if we look at the second order integrated rate equation, 1 over the concentration of A is equal to K times time plus 1 over the concentration of A, 0, Our slope is our K. So that would be the value of K for that expression. Okay, so now let's consider the decomposition of a compound called sulfuryl chloride, which in the gas phase can decompose into sulfur dioxide and chlorine gas. And so the reaction was studied at 593, and just to make that clear, right, that's Kelvin, that should be a capital K, right? And at that temperature, it was studied and found to be first order. And they found that 20% of the sulfuryl chloride would decompose in 80 minutes. And so our first question is, what's the rate constant for the reaction? Okay? Now, we had our integrated rate equation for a first order process, right? They told us it's first order. And so our integrated rate equation was that the natural log of the concentration of the final concentration divided by the initial concentration, right? Remember, that's all in the natural log, is equal to minus kT. If we don't want to deal with this minus, we can multiply both sides by -1, and we get the alternative expression, which is equivalent, that the natural log of the initial concentration divided by the final is equal to kT, right? That keeps us from having to deal with that negative sign in our calculation. Okay, so they told us that 80% or that 20% decomposed, right? So if 20% decomposed, then we can conclude that therefore 80% is left, right? And so we can use that to do our calculation. So to find K, we would start with, right, that the natural log of the concentration of A0 divided by 0.8 of that, 80% is left, is equal to our K times our 80 minutes. Right? And since these two things are the same, essentially we get 1 over 0.8, which is 1 1/4, right? So we have the natural log of 1.25 is equal to K times 80 minutes. So the natural log of 1.25 divided by 80 minutes is going to be equal to our rate constant, which is, if we calculate it out, 2.79 times 10 to the minus 3 per minute, if we calculate that all the way out. And so that's how we would find the rate constant in a 2-point integrated rate equation problem. Okay? Now we will use that in another problem immediately following. Okay, so we're continuing with the same reaction system, right? Our sulfuryl chloride decomposing to sulfur dioxide and chlorine gas. We were told the reaction was first order, and we determined that the K was 2.79 times 10 to the minus 3 per minute. And we're working with a first order process, so here's our first order rate equation. So our next question is, how much time will it take our reaction to go from 5 molar down to 3 molar? And we're assuming a reasonable number of significant figures here, right? So how would we do that, right? Now we know, right? We know the initial concentration, we know the final concentration let's see. Actually, I had intended to make a change here. To make our calculations just a little more straightforward, let's make this 2 molar. Okay, so we're going to go from 5 molar to 2 molar, right? And so again, we know, right, let's remind ourselves, we know our initial concentration, we know our final concentration, and we know our K, leaving time as our only unknown, right? And so if we're going to do our calculations here, right, we stick that in, we have the natural log of 5 molar over 2 molar, and remember that's all in the parentheses, is equal to K, which was 2.79 times 10 to the minus 3 per minute, times our elapsed time. So the natural log of 2.5, if we do our division, right, our division leaves us unitless there, divided by 2.79 times 10 to the minus 3 per minute would give us 328.5 minutes, which would be our elapsed time. So we can predict how much time it will take for a reaction to go from 5 molar down to 2 molar. Okay, so that's an example of a 2-point integrated rate equation problem with a first order rate equation. Okay, we're still dealing with the same system, right? Our decomposition of, let's undo that, our decomposition of sulfuryl chloride to make sulfur dioxide and chlorine. It's first order. We know the K, 2.79 times 10 to the minus 3 per minute. We know the first order integrated rate equation. So our next question is, what is the half-life time? Okay, for this first order integrated rate equation. Now, since we're dividing concentrations here, right, the units don't make a difference, but remember that at the half-life time, the concentration of our reactant final is going to be equal to 1/2 the concentration of our reactant initially. And so if we substitute that into our integrated rate equation, you get that the natural log of the concentration of A initial divided by 1/2 the concentration of A initial is equal to K times time, right? That divides out. 1 divided by 1/2 is 2. So you get the natural log of 2 is equal to K times the half-life time, right? So the concentration doesn't matter in determining the half-life time of a first-order expression. So really all we have to do is take the natural log of 2 and divide that by our rate constant, 2.79 times 10 to the minus 3 per minute. And if you do that division, you get 248.5 minutes, and that is equal to our half-life time for a first-order expression, right? So it's important that we remember this definition, right? That at the half-life time, that is true. Let me even add that to be clear. Right? So at the half-life time, right, that condition is going to be true. And so we can use that to our advantage. Here we're giving a reaction where our reactant A goes to products. We're told that it's first order and its half-life time is 32 minutes, right? So since it's first order, right, we can consider our first order rate equation. The natural log of our concentration of A0, or the concentration of A, equals KT. And so we know, right, at the half-life time that this ratio is 2. And so we can find K pretty easily here by, right? So the natural log of 2 divided by our half-life time, 32 minutes, will equal K, which if we do that math ends up being 2.166 times 10 to the minus 2 per minute. Right? That's what we get for K. Okay. Now, the problem continues to ask how much time would elapse if we went from 0.256 molar down to 0.0160 molar. Well, now that we know K and we know two concentrations, we can use our integrated rate equation. All right, so we can put those in there, and so you have the natural log of 0.256 molar divided by 0.0160 molar. And remember, that's all in parentheses. We're taking the natural log of that whole fraction, is equal to our K, which is 2.166 times 10 to the minus 2 per minute. And there's our elapsed time that we're trying to solve for, right? It ends up, if we do the math inside, right, that is 16, right? So we end up doing the natural log of 16 divided by 2.166 times 10 to the minus 2 per minute, right? That's equal to our elapsed time. And when we do that math, we end up with 128 minutes, right? Which is a perfectly good way of solving that problem. There's another way we could have considered it, though, too, right? If we'd have considered, if we start with 0.256 molar, if we divide that in half, we get 0.128 molar. If we divide that in half, we get 0.064 molar. If we divide that in half, we get 0.032 molar. And if we divide that in half, we get our 0.016 molar, right? We divided it in half 4 times. 1, 2, 3, 4. Therefore, our elapsed time will be equal to 4 times our half-life times, right? Since the half-life time is independent of concentration for a first-order process, so 4 times 32 minutes was the same 128 minutes that we got before. So we didn't have to go through the integrated rate equation if we realized that our concentration was the concentration that we would have gotten under, it was 1/16 of our initial concentration that counts as 4 half-lives. We could have worked it that way. So here we have a reaction where reactant B is going to product. We're told ahead of time that this reaction is second order, and that if we start with 0.256 that would be molar B, that the half-life time is 32 minutes, right? And so if it is a second order process, then our second order integrated rate equation is 1 over the concentration of B final minus 1 over the concentration of B initial is equal to KT, right? And so the first thing that we have to do then is find our value of K. Okay, so if we substitute in our concentrations, right, our final concentration of B is going to be 1/2 of our 0.256 molar minus our 1 over 0.256 molar, right, is equal to KT, where T is 1/2, and that's equal to K times our 32 minutes, right? And so that leaves us, right, K to solve for, okay? And so if we do a little math, right, a little algebra, right, here we get 2 over 0.256 molar minus 1 over 0.256 molar. That's equal to 1 over 0.256 molar. And that is equal to K times our 32 minutes, right? Our 1 over 0.256 molar is 3.90625 per molar. And so our K is going to be equal to that, 3.90625 molar divided by our 32 minutes. And to a reasonable number of significant figures there, we get 0.122. And that is, right, let me make sure I have my units right. Right, can't screw my units up. You guys are letting me get away with stuff. That was per molar. And so then you end up with per molar per minute as your units of your rate constant. And so we're going to end up with 0.122 per molar per minute as our rate constant. Okay, so now we're dealing with the same system, right? We still have a reactant B going to product. We were told it was second order. With the information we were given in the first part of the problem, we were able to find that our rate constant was 0.122 per molar per minute. Since it's second order, here's our integrated rate equation, right? And so our next question is, what would be the half-life time to go from the initial concentration we were given, which is, from a new concentration, 0.032 molar to 0.016 molar, right? And so we can put those concentrations into the equation. We know our rate constant now, right? We can put the concentrations in. We know our rate constant. We can find the half-life time, right? So if we substitute those in, then you end up with 1 over 0.016 molar minus 1 over 0.032 molar is equal to 0.122 per molar per minute. Make sure I get my units right. Right, per molar per minute, and that's going to times our half-life time, right? If we solve the left side of our equation, right, if we take those fractions and then subtract them, you get 31.25 per molar, right, divided by the 0.122 per molar per minute, right? The 1 over molar cancels, leaves us 1 over minutes in the denominator. When we divide, we invert and multiply, and so we get then units of minutes, and we find out that the half-life time is 256 minutes for that interval, right? And remember, the half-life time was 32 minutes for this system when we started with 0.256 molar. So this reminds us that the half-life time for a second-order process gets longer as we start with less and less material, right? Now, right, so we have to remember what happens with half-lives. We'll deal with that same system again, right? So reactant B going to product. We know it's second order. We know the rate constant. We know the integrated rate equation for that second order process. And so now our question is, right, how much time will elapse when we go from our high initial concentration down to a lower concentration, right? A larger change in concentration, okay? So we can, right, substitute those concentrations into our integrated rate equation, right? So we have 1 over 0.016 molar minus 1 over 0.256 molar is equal to our K, which is 0.122 per molar per minute, and our elapsed time, right? If we find the inverse of this and subtract from it the inverse of this, right? Remember our mathematical rules. Then you end up with 58.59375. I know I'm carrying extra significant figures here, and that's per molar is equal to 0.122 per molar per minute times our elapsed time. So 58.59375 per molar divided by 0.122 per molar per minute comes out to a reasonable number of significant figures, to 480 minutes as our elapsed time. So there are some examples of some problems with the integrated rate equation. You should be able to work through these with me and then go through and work problems on your own before the test on Wednesday.